Today we are going to learn about demystifying vanishing gradient problem. We'll explore its impact on deep learning models during backpropagation, uncover strategies to mitigate the problem, and enhance the performance of deep networks. By the end, you'll have a clear understanding and practical skills to improve your neural network models. Welcome to our exploration of the vanishing gradient problem. This phenomenon occurs when gradients used in the backpropagation algorithm become exceedingly small, effectively stalling the learning process. It's a critical issue in deep learning because it can severely impact the training efficiency and accuracy of neural networks. Understanding this problem is crucial for anyone working with deep models, as it affects how well a model can learn from data. In this video, we'll delve into how the vanishing gradient problem arises, its implications for neural network training, and strategies to overcome it. To understand the vanishing gradient problem, we must first comprehend how gradients function in neural network training. Gradients are the partial derivatives of the loss function with respect to the model's parameters. During backpropagation, these gradients are used to update the weights of the network, effectively learning from the data. However, when networks become deep, with many layers, the gradients can diminish exponentially as they propagate back through the layers. This is especially pronounced in networks with sigmoid or hyperbolic tangent activation functions. Mathematically, this can be seen when the derivative of the activation function is less than 1, causing the compounded product across layers to shrink rapidly. The result is that early layers learn very slowly, impacting overall network performance. Thus, the size of the gradient is crucial. If it's too small, the network stops learning effectively. The vanishing gradient problem can significantly hamper neural network training. When gradients become too small, the weight updates are negligible, leading to a slow training process and poor model performance. This difficulty in convergence particularly affects deep layers, rendering them unable to capture intricate patterns in the data. As a result, even with large datasets and extensive training times, the model may not achieve desired accuracy levels. This makes it imperative to address the vanishing gradient problem through effective solutions that facilitate the learning process and enhance the model's ability to generalize well.
Identifying the symptoms of the vanishing gradient problem is a crucial step in mitigating its effects. Typically, you'll notice stagnant loss values during training, indicating that the model isn't learning effectively. Additionally, you'll observe minimal weight updates, especially in the initial layers, which are often ineffective at capturing complex features. Deep layers fail to contribute significantly to the learning process, resulting in a network that doesn't scale well with additional layers. By monitoring training progress closely, you can identify these symptoms early and implement corrective measures to optimize the learning process. Activation functions play a pivotal role in the vanishing gradient problem. The sigmoid and hyperbolic tangent functions are particularly prone to this issue due to their properties. When these functions are used, the gradients can diminish significantly as they propagate back through the network layers. On the other hand, the rectified linear unit, ReLU, function has gained popularity for its ability to mitigate the vanishing gradient problem. ReLU maintains a gradient of 1 for positive inputs, preventing the exponential decay of gradients. However, it's essential to choose activation functions carefully and balance their use based on the specific needs of your neural network architecture. Proper weight initialization techniques can significantly influence the severity of the vanishing gradient problem. Starting with small initial weights can exacerbate the problem, as gradients become even smaller with each backward pass. Techniques like Xavier and He Initialization are designed to keep the scale of the gradients approximately constant across all layers, promoting better gradient flow. Xavier initialization is suitable for networks with sigmoid or hyperbolic tangent activations, while He initialization is ideal for ReLU activations. By selecting appropriate initialization methods, you can improve training efficiency and enhance the overall performance of your neural network.
Batch normalization is a powerful technique to address the vanishing gradient problem. By normalizing the inputs of each layer, batch normalization stabilizes the learning process and reduces internal covariate shift. This not only improves gradient flow but also enhances model robustness and allows for faster convergence. With batch normalization, models can use higher learning rates, accelerating the training process. By incorporating batch normalization into your neural network architecture, you'll ensure a more consistent and effective learning experience, ultimately resulting in better model performance. Skip connections and residual networks offer a pragmatic approach to overcoming the vanishing gradient problem. By allowing gradients to bypass certain layers, these techniques facilitate the propagation of gradients in deeper networks. This not only improves gradient propagation but also enhances network flexibility and learning capacity. Residual networks, or ResNets, have revolutionized deep learning by enabling the construction of extremely deep networks without suffering from vanishing gradients. The residual connections act as gradient highways, ensuring that information and gradients can flow freely throughout the network, leading to more effective learning and improved model performance.
In real-world scenarios, addressing the vanishing gradient problem often requires a combination of techniques tailored to the specific architecture of your neural network. It's crucial to customize solutions based on the network's depth, activation functions, and initialization methods. Continuous monitoring and adjustment during training are essential to ensure optimal performance. Leveraging advanced algorithms and techniques such as adaptive learning rates and advanced optimizers can further enhance the learning process. By studying case studies of successful implementations, you can gain insights into best practices and adapt them to your projects, ensuring that your models achieve their full potential. In conclusion, understanding and addressing the vanishing gradient problem is vital for anyone working with deep neural networks. By effectively mitigating this issue, you can enhance model training and performance. It's crucial to adapt solutions to the specific needs of your network, employing techniques such as proper initialization, batch normalization, and skip connections. As you continue your journey in deep learning, remember that continuous learning and improvement are key to achieving success in this ever-evolving field. Thank you for joining us in demystifying the vanishing gradient problem.